They have us surrounded, but we can't see them. Even though they light the way and keep our industry steaming full speed ahead. Pulled from the ground or right out of thin air, they take us higher and push us further. Now, Gas Tech on Modern Marvels. Blimps. We've all seen them. Hovering above U.S. cities during big games, or quietly circling any number of outdoor spectacles. From the ground, a blimp's graceful turns and steady course make it appear almost weightless. But in reality, what keeps the over 3 tons of metal and fabric of this Saturn lightship airborne is one very simple and visual use of gas technology. We're all familiar with gas. What makes balloons go up, the air we breathe, the fuel that helps us cook food, and dry clothes. But gas is actually a state of matter and totally dependent upon external forces to keep it that way.
Whether or not something can be in a gaseous state depends entirely on the conditions that it's under, its temperature and its pressure.
At the centers of distant massive stars, iron exists as a gas, while on Neptune's largest moon, Triton, nitrogen, which makes up over 70% of the air we breathe, is frozen solid. In our own small corner of the universe, the relatively stable pressure and temperature here on Earth allows 11 elements to occur naturally in gaseous form. But there are many more gases out there. Some are composed of different combinations of elements that form molecules, while other substances can be turned into a gas, such as water into steam, by adding heat or reducing pressure.
Gas has neither definite size nor definite shape. So if I take a gas and expand it into a confined shape, like a bottle or a glass, it will easily expand to fill that bottle, and it will take on the shape of that bottle.
That's because gas is composed of numerous molecules moving chaotically in all directions. And from that chaos comes, among other things, quite a bit of power.
The United States prospers and survives based on its use of energy, and predominantly that is fossil energy. About 94% of all the domestic energy is from fossil fuels. And of those fossil fuels, natural gas provides about a quarter of the energy.
This is because natural gas is made up of compounds that have carbon-hydrogen bonds. And in the presence of a high fraction of oxygen gas and at elevated temperature, those carbon-hydrogen bonds will react with oxygen to make carbon-oxygen bonds and hydrogen-oxygen bonds.
Simply put, natural gas is a great source of power because it burns, and very cleanly, producing 50% less carbon dioxide than coal and 25% less than oil. Composed mostly of methane, it develops in underground geologic formations from decomposing plant and animal matter. In the U.S. alone, the Department of Energy estimates that nearly 975 trillion cubic feet is trapped in subterranean reservoirs, and the only way to get to it is by drilling.
Because the easy-to-find oil and gas was exploited early, geologists and drilling engineers have had to go deeper and deeper to find additional resources, so that now the deepest gas is produced from over 25,000 feet, which is 5 miles into the earth.
We're now on the drilling rig floor. This is the real first step in the operational phase of being able to drill for and develop and produce natural gas. As you can see from the drill pipe located here, we're actually applying the rotational energy through a top drive system, which is more of a modern technology that we have. This allows us to drill more efficiently and more quickly. By utilizing a top drive system, we can vary the speed at which we want to rotate the pipe and to actually hoist the pipe up and down in a more efficient fashion.
Into the spinning pipe, the drillers pump a specially formulated mud, meant to lift pulverized rock and other debris out of the hole. This 6-inch diameter pipe is already 8,500 feet below the surface and is about to take a turn for the better.
This particular well is a horizontal well. The way that we're able to do that is we actually drill down to a certain predetermined kickoff point and put some tools into the ground which allow us to build an arc and actually go out into the horizontal plane. In a case like this, we'll actually drill a lateral out anywhere from 2,500 to 3,500 feet from this surface location. In some cases, we'll actually drill at higher than 90 degrees. We'll drill up a little bit. That will allow us over time, as we produce fluids into that lateral section, will allow those to gravity feed into the sump of the wellbore, more effectively get those out of the well, and ultimately increase the productivity of the gas.
But even with the guidance computers inside the rig's control room, for petroleum engineers, trying to find a gas pocket 2 miles underground with a 6-inch diameter pipe takes skill.
This is very similar to trying to hit a dot on the sidewalk using a very long strand of spaghetti dangling out of the top of the Empire State Building.
The business end of the drill rig is a 3-headed carbide steel bit that grinds its way through the rock.
This is a traditional tri-cone drilling bit. As you can see, the cones on the bottom. This is where we're actually able to break up the rock. We have drilling mud that's being pumped down through the drill pipe, comes out through the ports.
But simply punching a hole into the gas pocket doesn't guarantee a successful well. Rig workers rely on a topside injection process, known as a frac job, to coax the gas from the ground.
Over a mile below the ground is a formation that has the consistency of sidewalk cement. It's a gas-bearing formation, but in order to be able to produce the gas out of there effectively, we pump what we call a frac job, where we literally are fracturing the formation. We're injecting fluid at a high rate of speed into the formation along with some sand. The sand goes out inside the fracture and causes a flow path back into the wellbore to more effectively produce the gas. We do that by taking gel, pumping it into the formation. As you can see, it's relatively thick and has a lot of consistency to it. And we add into the sand. This actually sits into the formation, stays there, and allows a mechanism or a medium for the gas to flow into the wellbore.
What comes out of the ground is usually impure and must be processed before it can be used.
As far as the gas coming from the wells, we have thousands of miles of gas pipelines, anywhere from 2 inches on up to 24 inches, that gather the gas and bring it to the central facility. I kind of describe it like the spokes of a wheel, and the plant sitting in the middle of that wheel.
The first step for producers is to remove the groundwater in the gas. By putting the product in simple storage tanks, they allow the gas to rise while the heavier liquid sinks to the bottom. Raw natural gas is actually a combination of fossil fuels. The next step for producers involves separating and purifying each of the gases. Many complicated methods of separation, from pressure and temperature manipulation to chemical, are used, depending on the gas's composition. Here at the Devon Energy Bridgeport plant, outside of Fort Worth, Texas, the preferred method is cryogenic cooling. Inside of this 140-foot tall spire called the demethanizer tower, the gas is about to become a liquid.
Okay, in the demethanizer tower, we basically have the gas stream flowing up through it. At the right temperature, those molecules start gathering together and forming droplets. At a minus 170 degrees, just like rain, they start falling to the bottom of that vessel.
The liquids that form, such as propane and butane, move to these tanks for storage.
They represent a very small portion of our business, approximately 15%. The remaining 1.6 million gallons that we produce are sold down pipeline to the nation where they are distributed. The other 530 million cubic feet per day that we bring in as natural gas is sold as methane to the residential and industrial users throughout the area.
But getting the gas out of the ground and into a tank is only a small part of the story. Throughout history, a long line of evolving technology has made this one-time explosive oddity into the fuel of tomorrow. Over 90% of the natural gas used in the United States is produced domestically. Gas Tech will return on Modern Marvels. We now return to Gas Tech on Modern Marvels. Today, natural gas supplies the United States with over 20% of its energy. 1.1 million miles of pipeline crisscross the country, making the use of natural gas as easy as turning the knob on your stove. The exploration, drilling, and processing of this fossil fuel into a clean-burning source of power has helped mold the modern world. But natural gas has been impacting human life for as long as we have walked the earth.
Probably all through history, natural gas has seeped to the surface, and when it does, it's likely to be ignited. Supposedly, the Oracle of Delphi was, in fact, consulting with a natural gas flame. And it's possible that the burning bush that's mentioned in the Bible was, in fact, a naturally ignited gas seep.
But while the Western world was captivated by the natural phenomenon, a civilization in the East was looking for a way to put natural gas to work. Around the 3rd century BC, Chinese salt producers used bamboo to drill for and transport natural gas, which they used as fuel to evaporate their brine. But despite their limited success, the collection, transport, and storage of natural gas was so difficult, the fuel remained almost unusable.
From the time when the Chinese were drilling for and using natural gas in 300 BC until about 1800, there evidently was no need or interest in developing natural gas commercially. It existed as an oddity escaping in various places from the earth, but there was no use for it, and therefore there was no need to drill for it.
But during the 1850s, another more manageable form of gas opened the public's eyes to the potential new power source. Manufacturers used a product known as coke to fuel their furnaces. Coke was made by cooking coal in an airtight container. The final product burned hotter and more efficiently than coal. One of the byproducts of the cooking process was a flammable gas.
In the early 1800s, a manufactured gas was found very valuable to light street lamps. However, this manufactured gas is rather polluting, and when the opportunity came to use natural gas, which is much cleaner, it was considered a very significant improvement. The only problem was that most of the natural gas was located far from the cities that had the use for it as street lighting.
Petroleum companies could easily load their liquid products onto trains or trucks, but that didn't work for invisible, odorless gas.
It wasn't until pipeline welding was perfected about the time of World War I that gas could be transferred significant distances. Then, of course, the economic downturns during the Depression and World War II meant that there was not significant demand for natural gas. And it was only after World War II where both the need and the technology to transport gas coincided that we have a significant increase in natural gas use.
The timing was perfect. The consumer world was about to take a giant step into the future, and natural gas would provide both the power and the product.
And it was opportunities such as plastics that developed in the 50s that really stimulated gas use. Natural gas is both the fuel to run plastics factories and is the raw material that is used to make the plastic that was so significant in our lifestyle changes since the 50s.
Between plastic and pipelines, natural gas was no longer an alternative fuel. It was becoming as big a part of consumers' lives as gasoline and electricity, and its use would continue to grow. Today, that growth has led to a wide range of natural gas delivery systems. This strange-looking tanker ship is transporting over 125,000 cubic meters of natural gas, which will be unloaded at a specialized terminal. But most of the natural gas we use arrives via a complicated array of pipelines and distribution centers that push the product to consumers around the country.
Southern California Gas Company is the largest local distribution company in the United States. We serve approximately 20 million people through about 5.4 million meters. That's a service territory of about 25,000 square miles, which is most of Southern California. On an annual basis, we move about 1 trillion cubic feet of gas, which is a little less than 5% of the total gas consumed in the United States.
The natural gas enters the system from the producer's 30-inch diameter interstate pipeline. Though under pressure, the natural gas moves slowly. For distributors, forecasting how much gas their customers will use is an important part of the job.
We're here right now at our gas control center in Southern California. And at this location, we actually monitor where gas is going to come in, and we forecast where the gas is going to be used by our customers. So every day, we have to move the gas around our pipeline system to be sure it's in the spot that the customers need it. And again, with the gas moving relatively slow, we do have to forecast carefully and understand our customers' needs.
To make sure there are no gaps in the service, distributors around the country keep a little extra natural gas on hand. Thanks to over 400 storage facilities nationwide, if demand picks up suddenly and the supply in the pipeline is insufficient, distributors can quickly draw from nearby reserves. This is one of the largest natural gas storage facilities in the western United States. What makes this site, conspicuously absent of tanks and steel pipes, so valuable is the geologic rock formation over 10,000 feet below the surface.
The reason the storage reservoir is here is because 2 miles beneath my feet is this kind of rock. This is a porous sandstone. 20% of this rock is pore space, just like the space between the grains of sand on the beach. And that's where we compress the gas and place it in that porosity. We can fit 50 cubic foot of gas into every cubic foot of the rock. This is an impermeable shale. 200 foot of this shale sits on top of this sandstone, and that's what seals the gas in place, so it's there for us to deliver when we need it.
For natural gas distributors, getting the gas back into the ground takes almost as much work as getting it out in the first place.
Behind me is the main compressor building. We've got 5,500 horsepower units in the building. Right now, 3 of them are operating, and they're injecting 125 million cubic feet of gas per day. This gas is being picked up off the pipeline at about 600 pounds per square inch pressure and being injected into the ground at over 3,900 pounds per square inch of pressure.
To put things in perspective, our storage capacity is large. It's enough gas to serve the 20 million consumers in Southern California for about 3 months.
When the natural gas is needed, it's pulled from the ground and gets a good cleaning. Separation tanks and cooling towers, similar to those used in the initial refining process, remove dirt, water, and heavier hydrocarbons that have contaminated the gas while underground. Once back in the pipeline, the product is odorized and continues its journey to the customer.
Once we get near the homes, we run individual lines to each home. Those are very small diameter lines, usually in about a ½ inch diameter. When the gas gets to your home, it actually is about 1/3 of a pound pressure because we have a pressure regulator at the house adjacent to the meter that you see at your home. This is the device that our meter reader looks at when they come around monthly.
Surprisingly, most of the natural gas we use never comes directly to our homes.
We bring in about 3 billion cubic feet on a daily basis. About 1 billion of that goes to residential and small commercial customers. The other 2 billion go to the large customers.
And those large customers use natural gas in power plants to produce electricity and in all forms of manufacturing. Manufacturing that helps make up the world in which we live. In the end, the product that captivated early humans as it leaked from the ground now powers our world. But not all gas power relies on the burning of fossil fuels. Some gases are able to create energy simply by coming together. And the simplest gas, hydrogen, may soon prove to be the most powerful of them all. In 2002, the United States consumed over 23 trillion cubic feet of natural gas, the volume of a cube, almost 5 miles on each side. Gas Tech will return on Modern Marvels. We now return to Gas Tech on Modern Marvels. One of humanity's earliest uses of gas technology as a power source came with the invention of the steam engine. First built in the late 1600s, its rapid evolution changed the world by providing the power that turned the wheels of the Industrial Revolution. But in these early engines, gas didn't create the power. Wood and coal were burned to turn liquid water into something the machine could use. Steam. Today, hydrogen, the H in H2O, is about to participate in another revolution. And even though it's the simplest chemical element and the lightest, most common gas in the universe, it's about to turn the world upside down.
The credit for the discovery of hydrogen usually goes to Henry Cavendish in 1766, who described the properties of it, and sometimes to Antoine Lavoisier, who shortly thereafter actually named it hydrogen, from hydro, meaning water, and gen, meaning generation, because when you take hydrogen and oxygen, it makes water.
But engineers have learned that the two gases can also be used to generate a clean source of power in a device called a fuel cell. The result is a potential source of energy that uses two of the most plentiful elements on the planet, and whose only byproducts are heat and water.
The invention of the fuel cell is credited to Sir William Grove in 1839. So it's, 165 years ago. And there never was, for a century, really, a application of it that could be found that was sufficient value to the marketplace that you could call it a commercial product. I think it was really not until the 1960s that General Electric was able to develop fuel cells that NASA used in the Gemini missions, and then United Technologies Corporation developed a fuel cell for use in the Apollo missions.
Though launched into space atop a pillar of burning gas, once aloft, the space capsules needed power of a different type. Onboard computers and life support systems needed electricity, but the traditional means of generating power involved combustion, an impractical and potentially dangerous option in space. Fuel cells seemed ideal, and they had additional benefits.
Hydrogen combined with fuel cells were very attractive to NASA because you could generate electricity very efficiently, and obviously spacecraft need a lot of electricity, but you could also generate water, and that could be drunk by the astronauts, and that was also kind of 2-for-1, and made hydrogen fuel cell combination very attractive.
Today, car manufacturers are following NASA's lead. Since the early 1990s, automakers have steadily improved hydrogen cell technology. Modern fuel cells are composed of a positively charged electrode called a cathode and a negatively charged electrode called an anode, separated by a thin plastic membrane. When a hydrogen atom composed of an electron and a proton passes over the anode, it separates. The proton passes through the plastic membrane, but the electron cannot, and is sent as electricity through a circuit as a source of power, eventually reaching the cathode. Once there, the electrons and protons combine with oxygen gas. Ultimately, the fuel cell offers a power source with only heat and water as byproducts. But while hydrogen offers promise as a fuel, there are still many technological hurdles to overcome. The gas is extremely volatile, and scientists are trying to discover a way to store large quantities without potentially explosive high pressurization. But the biggest obstacle for engineers trying to create this ideal power source has less to do with the fuel cell than the gas itself.
Well, the biggest problem with hydrogen production is that today, 95% of hydrogen is made from natural gas. And natural gas is a fossil fuel, and when you turn natural gas into hydrogen, you release a great deal of carbon dioxide, which is the principal greenhouse gas that causes global warming. So you don't really solve our problem of dependence on fossil fuels, and you don't solve our global warming environmental problem by making hydrogen out of fossil fuels. The goal, the dream, is to make hydrogen out of renewable resources like wind power, solar power, and the like. The problem is that is a very expensive and inefficient process.
Fuel cells work because the other gas in the cell, oxygen, is one of the most reactive substances in the universe, causing our cars to rust and fruit to mold, but also keeping us alive by reacting with our blood. Its properties make it one of the best known and most used gases. Everything from steel production to medicine, and even rocket fuel, rely on oxygen's reactive molecular structure.
Oxygen was discovered as a major part of the Earth's atmosphere by Joseph Priestley, who did a series of experiments that he published in 1776. And these experiments began by toying around with burning candles in jars filled with air. And he quickly decided to move from candles to mice for reasons that escape me. And his critical experiment that he did was to put a mouse inside of a jar full of normal air and to note that the mouse would stay alive and active for 15 minutes. He then produced a jar of oxygen gas, and the mouse lived for an hour. So noting that the mouse lived 1/4 as long, he suggested that air is made up of about 1/4 of O2 gas, and that's close to the correct amount. And by the way, the mouse lived. He claims that he took the mouse out of the jar at the end of the hour and warmed it by the fire, and that it survived.
Within 100 years, industrialists such as steel producers began to recognize the advantage of oxygen's reactive nature. Pumping air through molten metal makes it stronger by causing the impurities to oxidize and separate out as fumes, or as a crusty material called slag. For steelmakers, pumping pure oxygen was even more beneficial. With demand growing, scientists around the world began looking for ways to pull mass quantities of the gas right out of the air. Today, that process has been perfected by air gas distributors, such as the British Oxygen Company, or BOC. With 43,000 employees in over 50 countries and nearly $7 billion in annual sales, BOC is one of the largest suppliers of industrial gases in the world. Here at the BOC processing plant in Braddock, Pennsylvania, nearly 58 million cubic feet of gas are produced every day. The plant's production can be summed up in 2 words: clean and cold. The challenge for the plant operators is to bring the temperature of the ambient air down to the point at which it will liquefy.
Our process starts at the air filter, which is the corrugated wall behind me. Inside there is filter elements which filter out the dust and the dirt. From the filter housing, it enters into the compressor via the corrugated pipe. The compressor has a 33,000 horsepower motor on it. It will flow up to 12 million cubic foot an hour.
The compressors push the air through the system, but compressing air causes it to get hotter.
Once we compress all the air and the gas, we have to cool it back down. That's the basic function of this piece of equipment. We circulate water through the system at 22,000 gallons a minute to our compressors, which picks up the heat out of the air and the product. We return the water back to the top of this tower, which sprays out over packing to disperse the water. We induce the draft up through with fans, and just that contact and the evaporation of the water cools the water back down again.
The air, or unrefined product, then heads to a cooling tower to further lower the temperature through evaporation.
The silver tower behind me is used to cool the air after it leaves the compressor. Air leaving at approximately 170 degrees Fahrenheit enters the tower in the base. The water is sprayed down over top of it, and the air comes out at the top of the tower at approximately 47 degrees Fahrenheit.
The air then passes through a chemical process to remove CO2 and water vapor, both of which, if left inside the airstream, would freeze, plugging the machine. The air then enters an expansion turbine, where most of the cooling occurs. Just as an aerosol can becomes cold when its pressurized contents are released, the expansion turbine, as its name implies, allows the gas to expand, which reduces its pressure, causing it to shed heat. The final step in the process involves distilling the gas into its individual elements.
The 170-foot tower behind me is where the actual distillation occurs. As the air enters in at minus 270 degrees Fahrenheit, we keep chilling the air down until it hits the liquefaction point of oxygen. The liquid oxygen forms, gravity takes over, argon and nitrogen gas continues up the column. Argon's next, it liquefies,
falls back down, nitrogen continues up to the top of the column.
From there, the separated gases travel to storage tanks. This BOC plant uses a pipeline to ship oxygen to its largest customer, a local steel mill. Trucks and train cars are used to transport to smaller customers. But carrying cryogenic liquid takes a very special big rig.
The trailers we use are like a big thermos bottle. You have an aluminum tanker inside, and you have a steel vessel outside. It's filled with an insulation material called perlite. The product that leaves this site as a liquid is put into a truck, as you see behind me filling. We'll fill it up to just under 80,000 pounds. Driver pulls onto the scales, hooks up the hoses, he'll program his scales, and once everything is verified, he'll start filling. At a certain pre-programmed limit, the scales will shut the valves, and the drivers will take a final test and button the trailer up.
But while some gases work because of their ability to react, others are prized for doing just the opposite. And the noble nature of a small number of gases, such as helium, best known as the gas that makes blimps slowly rise, is also responsible for the fastest and highest flying technology ever built. During launch, the Space Shuttle's 3 main engines consume around 60,000 gallons of liquid hydrogen and liquid oxygen every minute. Gas Tech will return on Modern Marvels. Helium, neon, argon, krypton, xenon, and radon are the 6 elements known as noble gases. Noble because they don't react with anything. At the molecular level, these gases have even numbers of electrons in their outer shells. This means they're stable and won't try to share electrons or react with other elements. One of the most widely used noble gases is helium. From party balloons to blimps circling overhead, we're all familiar with helium's lighter-than-air characteristics.
Its specific gravity is 0.138. Now, specific gravity is its relative weight to air, air being 1.0. So if you put helium in air, it will naturally rise to the top. And in fact, it'll eventually rise and float out of the atmosphere. That's why there's such a small amount of helium in the atmosphere, is because it's continually floating and going out into space.
Here on Earth, the gas is mainly found underground, within natural gas deposits. But in space, the main production centers are stars.
The helium was first discovered by Pierre Jensen in 1868 by looking at emission spectra from the sun. And he noted a yellow emission line in the spectrum, and it did not correspond to the emission line of any known element. And he suggested that it was emitted by an element that's unknown in the Earth, but was common in the sun, and he named it after the sun god Helios, so he called it helium. He was laughed at. It was considered ridiculous to identify an element in nature without having isolated in the laboratory.
Despite the gas's undignified discovery, within 50 years, the United States government began to see helium's serious military potential. Near the end of the First World War, the U.S. commissioned a fleet of helium-filled balloons to perform reconnaissance missions against the Germans.
The original reason the government got into the helium business was for observation balloons used during World War I for artillery spotting in Europe. The advantage to helium, of course, is that it's non-flammable. And you can shoot at that observation balloon, you just put a little hole in it, and it'll slowly come to the ground, and everyone walks away.
In the late 1920s, the U.S. government began building the Akron, and soon after, the Macon, held aloft by 6 million cubic feet of helium each. The rigid airships were the largest in U.S. history. Dirigibles continued their military service into the Second World War. During the invasion of Normandy, special helium-filled blimps called barrage balloons protected ships from attacks by the Luftwaffe. But over time, the government's real interest in helium was sparked not by how it reacted under fire, but how, as an industrial gas, it didn't react at all. Aerospace engineers in the 1950s pushed the limits of metallurgy in their quest to build ever faster aircraft. Both extremely light and exceptionally strong, airframes built from titanium opened the door to supersonic flight. But welding the metal together proved difficult. Welders who use electricity, such as in arc welding, must be wary of reactive gases. As the electricity melts the metal, gases in the air react to the charge, causing impurities that weaken the weld. By pumping non-reactive helium through the melting titanium, aerospace engineers in the 1950s were able to get welds so strong, it was as if the pieces had been forged from a single sheet of metal. The military found other uses for helium as they constructed weapons for the Cold War.
During the beginnings of the Cold War, helium really came of age and was used in great quantities in the Titan missile program and in the Atlas missile program as a purge gas and as a leak detection gas used in the fuel systems for those missiles.
For engineers, helium is the perfect choice when it comes to looking for holes. The second element on the periodic chart, which denotes its minuscule atomic weight, helium is structurally one of the smallest atoms. That means it can leak out of holes that are too small for water, or even other gases to fit through. Sometimes it leaks right through seemingly solid material.
Even though solid substances seem impermeable to helium, they are not. If we take just a regular latex balloon, fill it with helium, we can take this device, which is a handheld helium leak detector, hold its sniffer near the surface of the balloon, and we can detect the helium that diffuses through the balloon.
By the late 1950s, helium had become so vital to national defense, the government wanted to make sure it never ran out. Fortunately, the U.S. was home to one of the richest natural helium reserves in the world, the Hugoton Natural Gas Field, located deep in the rocks below the Texas and Oklahoma panhandles and parts of Kansas.
The Hugoton gas field was the major producer of natural gas for the United States. It contains about 0.6% of helium, and the government recognized that if something wasn't done quickly, that helium in that natural gas would be lost forever. And that's what prompted the Congress and the administration to get together and pass the Helium Privatization Act of 1960.
Under Congress's urging in 1962, the Bureau of Land Management converted a depleted gas field outside of Amarillo, Texas, into the Bush Dome Reservoir.
The Bush Dome is kind of a confusing term. It's not really a dome or anything you can see. It's a geological formation about 3,000 feet underground. It covers about 11,000 acres from the surface, and what it consists of is a layer that's about 500 to 1,000 feet thick of dolomite rock, which is a porous rock. And the gas is actually stored in the rock like you would store water in a sponge. On top of the dolomite rock is the anhydrite rock. It's very hard, it's not porous, and it acts as a cap, and is often called the cap rock.
Over the course of 9 years, the government bought the helium byproduct from public natural gas producers. By the early 1970s, it had entombed over 36 billion cubic feet of gas.
This right here is a Bivens A6 well. It's the richest helium content well in the world. It runs about 3,500 feet to the bottom formation, and the natural pressure on this is probably just a little under 600 right now. Due to the injection and withdrawal and the high content of helium now, it's a 72% helium well.
But with the passing of the Cold War, the government's need for helium diminished. Today, it's private industry that keeps the helium trade going strong, and the Bush Dome in business. Helium is used in many high-tech fields. Its extremely low boiling point makes liquid helium an ideal coolant for the magnets in MRI machines. But helium is mainly used by manufacturers of computer chips and fiber optic cables, whose success depends on keeping even the smallest contaminants out of their products. American industry uses roughly 5.5 billion cubic feet of helium every year. And the Bush Dome, which once paid producers top dollar to buy the gas, now receives payment from the same producers for storage space rental. But not all gases work their invisible magic behind the scenes. And some eye-popping new technology is pushing another group of gases to an electrifying future. To prevent deterioration, the Declaration of Independence is kept in a sealed titanium and glass container filled with a noble gas, argon. Gas Tech will return on Modern Marvels. We now return to gas tech on Modern Marvels. Neon, mercury, helium, xenon, and krypton create the spectrum of colors we collectively refer to as neon lights. From the sacred glow of an all-night wedding chapel sign to the gaudy glitz of the Las Vegas Strip, these gas lights have changed the way we see the world. That's because electricity excites the electrons of the gas, causing them to give off photons, which we see as colored light.
So the way that a neon light bulb works is by discharging electricity through neon gas. The neon gas begins with its outermost shell of electrons in a relatively stable or ground state. It's analogous to the state that this book is in when it's lying flat in my hands. It's difficult to move and nudge about, and it's as low as it can get. When the electricity passes through the gas, it pumps up those electrons into a higher energy state. And when the electricity has passed, the electrons fall back down to their ground state, and just like a sound is emitted when the book hits my hand, light is emitted when the electrons fall back down to their initial states.
A plasma ball is a type of neon light that seems to capture electricity itself. To make one of these glowing balls come to life, light makers carefully mix a number of gases. But first, they must make sure they start with a clean slate, or at least an empty globe.
We put it on a vacuum system and pump all the air out and try to get it as pure as possible. Often we'll bake them at up to maybe 700 degrees for an hour. Get all the impurities out, because it's very important. Impurities can contribute a lot to the mixture. Then once that's been done, then we backfill into this vacuum we've created.
At the center of the ball, a stainless steel core connected to a power source acts as a contact for the gas. As xenon and krypton fill the vacuum, a faint glow begins to appear.
Well, we put in our base mixture of xenon and krypton, and now we're backfilling it with neon gas. And that'll give us the body of the mixture with the arms.
The spider-like arms that develop inside the ball are manipulated by altering the power input.
This is a frequency adjust. I can actually attune the power supply to the globe. And different globes will vary, or different loads will vary. So then we have a finished globe. This is ready to go to a children's museum in Mexico City.
But not all gas lights are meant to be colorful. Fluorescent and halogen lights are highly efficient and last much longer than conventional bulbs. Fluorescent lights work when electricity turns a small amount of liquid mercury into gas inside the sealed tube.
So fluorescent light bulbs work by discharging electricity through a mixture of argon gas and mercury vapor. The electricity pumps the electrons in the outer shells of the mercury atoms into an excited state, and when they cascade back down to their ground state, they emit ultraviolet radiation. This ultraviolet radiation is then absorbed by a powder on the inside wall of the light bulb, and then that compound emits visible light.
Stimulating the phosphorus takes far less energy than in a conventional bulb. That means even though fluorescent lights contain hazardous mercury, they are usually considered environmentally friendly because they save electricity, which reduces power plant emissions. Halogen lights are even more advanced. In a typical light bulb, electricity passes through a filament, causing it to burn and glow.
So, for example, the most common form of light bulb is a little strip of tungsten metal that you pass an electrical current through until it heats up to the point that it incandesces or gives off light. If you were to do that in oxygen, in normal air, the tungsten wire would oxidize and make tungsten oxide, and it would burn out in seconds. If you do it in the presence of argon, which is what fills many light bulbs, then it will be unreactive and will persist, won't oxidize.
Thanks to the gas inside the bulb, the filament can last for years, allowing these lights to be economical and efficient, while also offering us a future that is both brighter and cleaner. The power and preservation of this simple state of matter affects our lives every day. And whether it's lighting a room or running a power plant that lights an entire city, gas technology has us surrounded every step of the way.